We'll start in 1 minute. Today we'll be in section 11.9 on representations of functions as power series. And a reminder, test 4 will be next Friday, and it will be over sections 1 through 9 from chapter 11. Functions as power series. It is useful to represent certain types of functions as power series. A well-known power series for the absolute value of x less than 1, we know that 1 plus x squared and so on. In sigma notation, the terms are x to the n as n ranges from 0 to infinity. This is a geometric series, and if the absolute value of x is less than 1, the sum is 1 over 1 minus x. All we have to do is apply the geometric series formula. The common ratio is x. The number a is 1, so this is like a divided by 1 minus the common ratio r. So that means the function f of x equals 1 over 1 minus x can be written as a power series. For this particular power series, the partial sum s sub n is a degree n polynomial function, 1 plus x squared, and so on, up to plus x to the n. Okay, so we're going to use this fact, use 1 over 1 minus x equals 1 plus x squared, and so on, to write other functions as power series. Before doing this first example, f of x equals 1 over 1 plus x, I'll just show you something. Suppose we have 1 divided by 1 minus a function f of x. I don't really need to put the brackets around f of x, but just wanted to make sure that the denominator is 1 minus a function f of x. If we use long division, that is, divide 1 minus f of x into 1. 1 goes into 1 time. And then if I multiply 1 times 1 minus f of x, I get 1 minus f of x. In long division, we subtract. 1 minus 1 is 0. Above the minus f of x is 0. 0 minus a negative f of x is positive f of x. Okay, then the next cycle in the long division, 1 goes into f of x f of x times. And then we multiply f of x times the divisor. So f of x times 1 is f of x. And then we're going to subtract f of x times f of x. So in other words, we're going to subtract the function f of x squared. And then we subtract f of x minus f of x is 0. Up here we have 0. 0 minus negative f of x squared is f of x squared. And then 1 goes into f of x squared, f of x squared times, and then f of x squared times the divisor, we get the function f of x squared minus the function f of x to the third. And by now, you no doubt see the pattern. So 1 over 1 minus f of x can be written as a series, 1 plus f of x plus f of x squared and so on. And then in sigma notation, we can write it as the sum from n equals 0 to infinity of the function f of x to the n. And this converges. We're treating it as a geometric series, so it converges if the absolute value of f of x is less than 1. Pretty neat. So that's the idea that we're going to employ to find power series for certain functions. And in some cases, we might need to do a little bit of rearranging. Maybe rearranging isn't the best term, but a little bit of altering without changing the function. Okay, so if we want to use 1 over 1 minus x equals 1 plus x squared, and so on, then 1 over 1 plus x, we think of that as 1 over 1 minus negative x. And then we just put negative x inside each of those x's in the formula above. So we write this as 1 plus negative x to the first plus negative x to the second plus negative x to the third plus negative x to the fourth, and so on. And then we can simplify a little bit. The number negative x to the first is negative x. So we can, instead of writing 1 plus negative x, we write 1 minus x. And then the next one is plus x to the second. The next one after that is minus x to the third. The one that follows that is plus x to the fourth. After that is minus x to the fifth, and so on. And then in sigma notation, we can write this as the sum when n starts at 0 and goes to infinity. And it's an alternating sequence, or an alternating series, I mean. So it's negative 1 to the n times x to the n. Okay, so this converges. This converges when the absolute value of negative x is less than 1. but the absolute value of negative x is just, that's the same as the absolute value of x is less than 1. So the radius of convergence is 1 in this case. Okay, well, now you know what to expect. Now we're just going to do a few examples. So what do you think we're going to do for finding a power series representation for this function, f of x equals 1 over 1 minus x squared? Okay, we're using this as our template. But as was illustrated earlier, if we have 1 over 1 minus f of x, then the power series representation is 1 plus f of x plus the square of f of x plus the cube of f of x, and so on. So in this case, the f of x is just x squared. So we write 1 plus x squared to the first plus x squared to the second plus x squared to the third, and so on. And then we'll just write it in the normal way, 1 plus x squared plus x to the fourth plus x to the sixth, and so on. And in sigma notation, the series, this will begin at n equals 0, and the terms are x to the 2n. Okay, so when will this converge? This converges for what values of x? Well, our function is x squared, so the absolute value of x squared is less than 1. But this means same thing as the absolute value of x is less than 1. Okay, so the radius of convergence is 1. And the interval of convergence is from -1 to 1 with excluding the endpoints. All right, so the next one is, this function is 1 over 1 plus x squared. So we think of this as 1 over 1 minus the negative of x squared. Then we use the same template. So this is 1 plus negative x squared to the first plus negative x squared to the second plus negative x squared to the third, and so on. Then to simplify, we'll get 1 minus x squared plus x to the fourth minus x to the sixth, and it will follow that alternating pattern. The next one will be x to the eighth and minus x to the 10th, and so on. Okay, so the power series in sigma notation start at n equals 0. It's alternating, so we have to have -1 to the n. and then x to the 2n. This will converge. Let's see, our function this time is negative x squared. So the absolute value of negative x squared is less than 1. But that boils down to the absolute value of x is less than 1. So the radius of convergence is 1. Okay, now that you've seen 3 examples, I'll give you a couple of minutes to try this one out. See if you can find a power series representation for 1 over x plus 2. Or if you don't know how to do it, let me know. Or if you think you're onto something, let me know also. So this involves an alteration. So what sort of alteration do we need? Okay, the first thing I'll do is write it as 1 over 2 plus x. And then in the denominator, first I'll factor out 2. So we get 2 times 1 plus x over 2. And then I'll replace the 1 plus x over 2. Since I have this factor of 2 in the denominator, that's the same as multiplying a rational expression by 1/2. So 1/2 times the rational expression 1 over 1 minus negative x over 2. So we'll retain the factor of 1/2, but then we'll apply the same formula that we used above to get a power series representation for 1 over 1 minus negative x over 2. Okay, so we have 1/2 times 1 plus negative x over 2 to the first plus negative x over 2 to the second, and so on. Next one plus negative x over 2 to the third. So we get 1/2. We'll simplify those expressions. So we'll get 1 minus x over 2. The next term we're squaring, so it will be plus x squared over 4. And then minus x to the third over 8. And so on. The next one, plus x to the fourth over 16. And then in sigma notation, we'll put the factor 1/2 on the outside of the summation. So this will be from n equals 0 to infinity. It's an alternating series. So -1 to the n. And the terms are what? So x to the n over 2 to the n. So there's something that's bothering me. Let's see. No, I think we're okay. But since 1/2 is multiplied by everything, we can distribute multiplication by 1/2 and write the series as from n equals 0 to infinity, -1 to the n, x to the n over 2 to the n plus 1. Hey, what about the interval of convergence? So this converges when the absolute value of -x over 2 is less than 1. That's equivalent to the absolute value of x less than 2. So the radius of convergence on this one is 2. Okay, let's move on to the next page. Find a power series representation of f of x equals x squared over 1 plus x squared. So any ideas on this one? Well, we're going to use one of the power series representations that we found on the first page. So we saw that 1 over 1 plus x squared so this one is 1 minus x squared plus x to the fourth, and so on. So in sigma notation, this is the series n starts at 0. It's alternating. And the terms are x to the 2n. Okay, so x squared over 1 plus x squared can be found if I just multiply both sides of this series by x squared. So multiply both sides by x squared. I'll just write multiply by x to the second. Then we get x to the second over 1 plus x squared equals x squared minus x to the fourth plus x to the sixth minus x to the eighth, and so on. And then the sigma notation let's see, it's alternating. So -1 to the n, and this will be x to the 2n plus 2. Okay, so that's all there was to that. Okay, in the next example, we'll use a partial fraction decomposition to find a power series representation for this function, f of x equals -2 over x squared minus 1. Yeah, I'll give you a few minutes. Find a power or a partial fraction decomposition for -2 over x squared minus 1. When you find it, it should be pretty easy to type in, relatively easy. Are you getting close to an answer? Well, for partial fractions, we want to factor the denominator. So we have -2 over x plus 1 times x minus 1, or sorry, -2 over x plus 1 times x minus 1. And then in partial fractions, we write a over x plus 1 plus b over x minus 1. A and b represent constants. So when we write it as a single rational expression with the common denominator, we have a times x minus 1 plus b times x plus 1 over x plus 1 times x minus 1. Okay, so ax minus a plus bx plus b over x plus 1 times x minus 1. And one step further, we can write, since we have ax plus bx, we have a plus b quantity times x, and then minus a plus b. Well, since the numerator is equal to -2, it must be the case that a plus b is 0. And -a plus b has to add up to -2. So -a plus b equals -2. When we add these two equations together, the a is eliminated, and we get 2b equals -2, or b equals -1. And if b equals -1, a has to equal +1. Okay, so we'll rewrite this rational expression as a sum of two rational expressions, 1 over x plus 1, and then minus 1 over x minus 1. All right, we'll do another rearrangement. 1 over x plus 1, think of that as 1 over 1 plus x. And minus 1 over x minus 1, think of that as minus -1 over 1 minus x. So in effect, you can think of that maneuver as multiplying 1 over x minus 1 by 1 in the form -1 over -1. And then a little bit more arithmetic. We have 1 over 1 plus x. Since we're subtracting a negative, we can write that as plus 1 over 1 minus x. We saw the power series representation for 1 over 1 plus x and for 1 over 1 minus x. So we'll rewrite those power series distributions or representations for 1 over 1 plus x. That's 1 minus x plus x squared minus x to the third plus x to the fourth, and so on. Add that to the other series, 1 over 1 minus x. This is 1 plus x squared plus x to the third plus x to the fourth, and so on. And for two series that converge, these two series both converge for absolute value of x less than 1. So we can add them. So we have 1 plus 1, that's 2. The minus x plus x is 0, so no x terms. And then plus x squared is plus 2x squared. And you see the pattern. The next term is plus 2x to the fourth, and then plus 2x to the sixth, and so on. So in sigma notation, we have 2 times x to the 2n as n ranges from 0 to infinity. This converges since both of the original series converge for absolute value of x less than 1, then the same interval of convergence for this new series. Okay, so -2 over x squared minus 1, power series representation. All right, the next thing to talk about is the Theorem 2 in section 9. So this theorem will be pretty easy to understand, but let's go ahead and read through it. If the power series about A, the terms are c sub n times x minus a to the n. If this power series has a radius of convergence, capital R, which is greater than 0, then the function f of x, that's what we get when we expand the power series. That function is differentiable and continuous on the interval from a minus r to a plus r. And we can compute the derivative, f prime of x. We just compute the derivative term by term of the power series representation for f of x. Okay, there's something wrong with this formula. Do you see it? Okay, well, let's see. When n is 1, we have 1 times c sub n. When n is 2, we have 2 times c sub 2. So I need the n times c sub n times x minus a to the n minus 1. So we need an n there. Okay, but when we integrate f of x, we do that term by term. This one looks correct. So integrate term by term and just use the integration formula for each of the terms in the series. Okay, so the radiuses of convergence of the above power series are both capital R. But the intervals of convergence may or may not include the endpoints. And so here's just a reiteration of what I mentioned earlier. Differentiating and integrating term by term in a series works provided that the series is a power series. For other types of series, it's not as simple as for power series. Okay, we'll do a couple of examples with derivatives and integrals in mind. Find a power series representation for f of x equals the natural log of 1 plus x over 1 minus x. Well, using a property of logarithms, let's rewrite this as the natural log of 1 plus x minus the natural log of 1 minus x. Okay, so this is our f of x, lowercase f of x. On the previous page was a theorem involving derivatives and integrals. If we compute the derivative of f, the derivative of the natural log of 1 plus x, what's that equal to? One over 1 plus x. And then we're subtracting the derivative of the natural log of 1 minus x. And the derivative of the natural log of 1 minus x with respect to x is negative 1 over 1 minus x. The negative 1 in the numerator is the derivative of the 1 minus x from the denominator, using the chain rule. And then we can write this as 1 over 1 plus x plus 1 over 1 minus x. 1 over 1 plus x plus 1 over 1 minus x, that's the series that we found using the partial fractions on the previous page. Okay, so we found that 1 over 1 plus x plus 1 over 1 minus x, I always forget. Let's see, it's 2 plus 2x squared plus 2x to the 4th plus 2x to the 6th, and so on. So in sigma notation, oops, sorry, we don't need it's 2 times x to the 2n. Okay, so how do we use this to find the power series representation for the natural log of 1 plus x over 1 minus x? We have the power series representation for f prime of x. We want the power series representation for f of x. So we just integrate. So the natural log of 1 plus x over 1 minus x is equal to the integral of this power series so we get a constant of integration and then plus 2x plus 2/3 x to the 3rd plus 2/5 x to the 5th, and so on. So this is equal to c plus, and then in sigma notation, We can start this one at n equals 1, I think. So it's 2 times x to the 2n minus 1 over 2n minus 1. So let's check to see if that works. When n is 1, 2 times 1 minus 1 is 1. So that's the first term. When n is 2, the exponent is 3. The denominator is 3. So it looks like that works. To find the constant of integration, we can evaluate this function when x is 0. So f of 0 is the natural log of 1 plus 0 divided by 1 minus 0. And that's equal to c plus the infinite power series. But if x is 0, the series is 0. And here we just get the natural log of 1. We know the natural log of 1 is 0, so the value of c is 0. So we can say that the natural log of 1 plus x over 1 minus x is this series. All right, let's try the next one. Find a power series representation for g of x equals 1 over x plus 1 squared. Hey, what are we going to do this time? Well, with a little practice, you'll learn how to notice some things. The denominator has x plus 1 squared. Maybe it's related to the power series of 1 over x plus 1. So I'll just call this capital F of x equals 1 over x plus 1. If we compute the derivative of this using the quotient rule, the derivative of 1 is 0. So 0 times x plus 1. And then minus 1 times the derivative of the denominator, which is 1. And divided by x plus 1 squared. And this simplifies to negative 1 over x plus 1 squared. Well, we want positive 1 over x plus 1 squared. So we can get that if we just take the negative of f of x. I'll call this capital G of x equals negative 1 over x plus 1. And then when we compute the derivative of capital G, we get x plus 1 squared. So capital G of x is the negative of 1 over x over 1 plus x. And this series is it's the negative of 1 minus x plus x squared minus x to the third plus x to the fourth, and so on. Distribute the negative. So g of x is negative 1 plus x minus x squared plus x to the third minus x to the fourth, and so on. And then to get the power series for 1 over x plus 1 squared, we just take the derivative of g prime. So the derivative of g, which is 1 over x plus 1 squared, we're going to get 1 minus 2x plus 3x squared minus 4x to the third, and so on. Okay, but we're out of time for today. We'll also be in section 9 on Monday. So go ahead and sign in for attendance.